Hello everyone, I am Andrii Mytroshyn, and now I will present you quite exotic team. It's a way of attack on CPU that is based on GPU. In more general case, it's a SIMD based attack. So a little bit about myself, small prehistory. I work in Samsung Electronics, mostly work with some GPU stuff. After that I work almost 5 years in Vistone, where I work with improving GPU performance. And now, almost a year and a half, I work with Carbon Black, where I also try to push this type of attack. And like 10 years ago, I was trying to work in cyber police. I passed theoretical, practical part, but didn't work because of some other reason. So, first question, who familiar what is SIMD? Okay. So, SIMD, it stands for simple instruction, multiple data. It means that we will process our data in parallel way. So, where SIMD is used? First of all, okay, it's not working. Most familiar is GPU. So any GPU, external or internal, they work in SIMD way. After that, like all ARM processor, they have a special extension for that is provide vector data calculation that is called Neon. Another CPU type is AMD and Intel. In general, x86, they have SSA instructions, streaming SIMD extensions. And now it's kind of popular, this square RV, it's RISC-V. Now they do not have a SIMD extension, but they work with providing it. So, the question is, who don't know, and this is almost all of the, this room, what the hell is SIMD? So on this diagram, I don't know why it's not working. Okay, so this MIMD. So what is mean? This is how our general CPU is working. So we have one piece of data, in this case 0, 1, 0, and we make some mathematical operations. And this is a good way because, like, for example, now in modern CPU we have 16 cores, and we could make 16 independent calculations. So it's not only like plus, minus, any calculation that is not related to one to another. So here, like normal instruction set, we have blue is like one instructions for adding, multiplication, copy, doesn't matter. Yellow, it's one piece of data, some value, and we have one piece of result. So everyone knows how it is work. And now we start working with SIMD. So SIMD provide similar way of work, but we have several pieces of data, and we provide one the same instructions for all of them. Like drawn here, so we have one instruction, for example, multiplying by 4, and several pixels where we need to do this stuff. And we will have several pixels as a result. The good way, so the best since what is happening, this is will make at once in parallel. So if we compare one execution as standard CPU, for example, like adding 2 digits, it will take, for example, 1 nanosecond. And here, when we will make like one additions for 4 pieces of data, it will also make this for 1 nanosecond. So it will take one piece of time for, it doesn't matter how we will add 1, 2, 3, 4, 16, doesn't matter. Yeah, it should be divided by 16 in general. So, why it was used originally? Originally, it was used for image processing. So, when you have your display, you display some stuff, and for example, you need to, so here you could see that, sorry, this left image, it's a little bit blurred. Here it's on the right side, it's a little bit sharpened. So how it is made? So we just apply for each pixels here one convolution matrix that is just processed in some way. And it's make, for example, here we have like 16 pixels. So for one, I don't know, like nanosecond, it will calculate first 16 pixels, second 16 pixels, and so on, so on, so on. So where it is used now? Yeah, so here is kind of very old way for using. Now GPU calculation is used, for example, for neural network training, for AI processing, for blockchain. In general, any stuff that could be parallelized and work. And it's need to be processed a lot of data. So how it is look in under the hood. So this is example of how to ARM CPU different generation is look like. So in general we have okay, this blue part. We have you see 1, 2, 3, 4. So it means like we have, for example, 4 core, and each core has ARM v7 30-bit 2 CPU for calculation, Neon a data agent, floating point, and some local cache. And after that, this part below, it's some memory bus for communication with external memory and external resources. The newer generation, Cortex-A720, has almost the same architectures. It has a little bit extension. Now we work not only with 32-bit, but also with 64-bit. We have bigger memory. We have additional caching, additional instruction, and so on. But again, we have the same bus, like asynchronous bridge with some extensions. For x86, the situation is same. We have this image, and you could see that kind of almost the same. And this layering means that we have like 16 or 32 cores. So okay, here kind of space shuttle or space station. So we have our CPU, we have our bridge, and we have memory, and some external GPU if we have. The main point of attack is this part. So when you're processing some data, you need to, because your CPU could not contain a lot of data, it has a limited amount of cache, for example, 32 megabit cache 3, level 3. Or for example, for level 1, it would be, for example, like 1 megabyte. But you need to process bigger images or bigger piece of data, like 100 megabyte. So you will each time copy this piece of data to your processing unit. So situation is CPU, but with GPU it has the same. So now modern GPUs, they kind of computer. They has own memory, own bus driver, own system for power supply, and so on. So when we write here GPU, it means that inside GPU we have a lot of this kind of similar architectures. And now is very interesting stuff. So for example, this, okay, I don't have mobile phone. So when you take your mobile phone, if it is like latest generation, probably it will have like 32 or 64 Neon cores that could process in parallel. It means that it could process it like really, really fast. But another point, like when you try to calculate some multimedia data, you could feel that your phone starts heating because it starts doing a lot of this copying data. So first time when I start working with GPU, I think, okay, so if it is kind of separate PC that has own data, so probably we could apply some kind of attack. And much interesting attack that I could solve from this using GPU is exhausting attack. Idea of this attack, we try to overload of usage of some part and expect that some other application will start work in strange way. And this is kind of example of such attacks that I saw in my experience. So first type of attack, it was happened on NVIDIA GPU. And when you have these SIMD calculations, you need to use some special language. Yeah, it's kind of based on C++, but with some extensions that they called vector extensions. And the NVIDIA GPU, it has support two external language, OpenCL and CUDA. This is language for computation, not for processing with data, with images. Yeah, you could after that transfer it to OpenGL, but in general, they made just for calculation. And the idea was we have a very big image, like 10 of megabytes, and make some processing in some way. And we saw that when we send this image to the GPU, and start calculating this data, that like each 20-30 seconds, computer is crashing and go to the blue screen of death. The reason was following: operational system, when it is work, so they has a lot of drivers in Linux. It's daemons who prefer what. But in general, GPU has a little bit different level of communication. They has some special API for refreshing your display. And operational system send some signal to the GPU and say, okay, you're active, could you refresh this screen for displaying something? And because of CUDA occupy all resources on GPU could not respond. Operational system sent one notification, second, third, and said, okay, this device is freeze, I need to restart it. So it was like 12 years ago. Another type of attack that I observed, it was happening in Visteon. So in Visteon, in a lot of clusters, we use Renesas chip, RCAR H2 and M2 generation. M2 it's kind of low range, and H2 it's high range. You could compare it like Intel, like Pentium and Celeron. So kind of the same, but with some limitations. So we just execute simple shader for just, I don't know, making pixels, transfer it from blue to pink, I don't know. Very simple stuff. And we saw that in some cases on this low-level chip, low-budget chip, they start producing some artifacts. So for example, we say, okay, these pixels should be pink, but we show that it start be yellow, for example. And we could not understand what's the reason, because the same chip is working on same shader work on another chip perfectly. The reason was pure implementation of the driver on the driver level. When they introduce a new driver, they think, okay, we are lazy, we do not want to spend a lot of time, so we will make it in some way. And in general, we need to use some tricks for avoiding these corner cases. Another situation was happening with neon calculation. So neon is when we have CPU and we do not bother GPU for some calculation. We send some instructions for example, for copying data. By the way, if you use simple C++ function for copy data, it's work slower than you do it with neon instructions. The difference would be like 15-20%. So just a simple copying data with neon will work like 15% faster. But from the other side, it will cause additional heat, because it will use another part of a SOC chip, and you will need to do a lot of transferring data. And another kind of interesting stuff is happening with OpenCL. So who know what is OpenCL? Okay. So OpenCL is a kind of standard language for calculation some data using GPU. So you have GPU, you write your application for calculating on GPU, you transfer some data from your RAM to GPU RAM, I'm talking now about external GPU. And you run this application and this makes some calculation. The same thing with CUDA. And NVIDIA is only one thing that is only one vendor who is using CUDA because it is their own property. But returning here to OpenCL. The situation was following. We write a simple application according specification. So like in specification, you have around 70 or 72 different API for like compiling program, transferring data, executing such stuff. And we saw that this program has different behavior on different GPU. Even worse for same GPU, but with different version of the driver. They have different behavior. The reason was the conformance test. This is a collection of tests that kind of says that, okay, your device is compatible with our standard. They check from all these 72 API, only 65 API. So 7 API is not checked at all. And this like 65 API that is checking, some of them checking in very strange way. For example, just call it once, it didn't produce any error with correct data, and so we could work. So almost all OpenCL drivers for CPU, GPU, and other FPGA, they do not compatible with each other. So you could not guarantee that one application will work on another device. And even worse, it's happened with CUDA. Because what NVIDIA thought, okay, we have CUDA and we should support OpenCL. And why we need to re-implement OpenCL in another way if we could just have our own CUDA and OpenCL will be based on CUDA. And in this way, when we will compare metrics, we will say, okay, our CUDA is work faster than OpenCL. And because of a different requirement for these languages, we saw it was like 12 years ago, I even write some ticket to NVIDIA that standard way, when you create kind of link to the application, it is failing on OpenCL. And it is failing on OpenCL because CUDA at that time was not supporting this functionality. So OpenCL part is working fine, but because under the hood it's used CUDA, CUDA didn't support it. And it's crashing. So that was my observation. And here it's like example of very interesting attack that was during the last year. So first attack, this is leftover local. So idea is you have your GPU, and when you training your LLM, or in general any neural network, or I saw some observation on some iPhones that if you render some stuff on your application, if you run in parallel another application and try read GPU memory, you could have access to memory from another application. So they share local memory between different applications. And in this case, I think you could imagine what it could cause. And this attack is still available on some iPhone devices. Another type of attack, this is a pixel stealing attack. This attack is based on wrong implementation of iframe in HTML WebDriver. I don't know how to say it better. So idea is when we try to use iframe from HTML language, someone call it language, they try to store this data in GPU. And because we have a similar attack to LLM, it's we could access to this data from another application from another memory. Here on cv.meter.org, you could also find a lot of GPU-related attack. And the last attack, it's a downfall bug. So this attack is present on Intel and AMD CPU. So all generation of Intel CPU between generation 5th and generation 11th of all of their device has this attack. You could just kind of type this downfall Intel, and you will see that it has a. I will not describe because I do not have a lot of time for a lot of such explanation. So in general, a main point of this presentation is just to show you that even some device that you think, okay, this is just for rendering stuff, for displaying it could cause a potential problem. I remember one, I forgot here to mention on previous slide, with OpenCL. Like 8 years ago or 7, I worked in Samsung, and we are writing some special application for displaying YouTube content from secure storage. So you have Qualcomm extension on, so we use Qualcomm chips in Samsung phones at that time. And we have special extension for trust zone. And Qualcomm say, okay, for accessing this data, you need to have this special certificate. After that, you have a kind of special OpenCL API for accessing this memory. And it will work fine. And as usual, we have strict deadline. We do not have time for reading a lot of, I don't know, hundreds of pages of this manual. So I said, okay, could I just try to access to this data using standard OpenCL API? And after 3 days of trying, I was able to bypass all this Qualcomm Trust Zone certificate and just access as plain memory. So any application could just open Qualcomm Trust Zone memory and read it without any security certification. We reported, I suppose that during 7 years that they was able to fix it. If not, no, I didn't say anything. Okay, in general, that's all. Do you have any questions?